and welcome back to Calculus 1, section 2.5, limits at infinity. So previous section was infinite limits, which means the answer was supposed to be infinite limits. Now, limits at infinity, you are looking for the answer once you consider x, which is approaching infinity. So, we are focusing at the situation where the limit x approaches either positive or negative infinity of a function is going to give us either finite value or one of the infinities. So this is the limits at infinity. So we are looking at what's happening at negative infinity or at positive infinity. Now this can give us two mathematical concepts. Again, both of these studied in pre-calculus 1, but not with limits. One concept is going to be the concept of horizontal asymptote, if you get these guys, and the other one is end behavior of the function if you get one of these puppies. I'm going to start with the end behavior, and then we are going to go and look at the horizontal asymptotes with a definition. So you have definition and a formula for vertical, and then you will have definition and formula for horizontal asymptotes. But before we get that, let's take a look at the end behavior. So end behavior of functions. So you have a function, let's say x squared, and if you look at these ends that are on the graph, but you know they extend infinitely, this end over here will say that the limit of x squared as x goes to positive infinity will be positive infinity. Because as you go infinitely to the right, this arrow will go infinitely high. Does that make sense? And then on the other end, over here, maybe I should use a different color for these arrows. And on the other end, we have that the limit as x goes to negative infinity, because it's going infinitely to the left, is also going to give you positive infinity. Hopefully that makes sense as well. Because as you go infinitely to the left, the arrow will still go infinitely up. So technically, each one of these functions where arrows go either up or down, right, will have these end behavior limits, and we can summarize that in this chart. You have four possible types of arrows. So x cubed will be using these two, x squared, the two on top, negative x squared, the two on the bottom. E to the x will have this one on the right. Log, square root of x, they're all going to have this one, right, going forever. So this goes for all functions that exhibit this behavior. Sine and cosine do not exhibit this behavior, because sine is going to be an infinite wave like this, and it will never go all the way up or all the way down. So not all functions fit this idea. Only those that will go forever, like exponential function goes forever, logarithmic function goes forever, square root function goes forever. So you have functions that will go forever, and then you have those that will not, like trig functions. So you have to be careful about that. But when you have these arrows, this arrow here, you can clearly, in your mind's eye, hopefully you can, decompose this motion into motion to the right forever and motion up forever. And to capture that with calculus, you simply write limit of whatever the function is, as x goes to positive infinity, that's the tendency to the right, the answer is positive infinity, which is the y value goes forever up. The one on the bottom, limit x goes again to positive infinity, because it goes to the right all the time, is negative infinity in the y because of the answer. And this is the way to describe the end behavior. Now, we did not describe it that way in your pre-calculus 1 book. We just said, oh yeah, the end behavior is up to the right, right? So you would know which way it goes. You can find the same chart in your pre-calculus book without the limits written all over the place. Now you have the limit x goes to negative infinity of f of x, which is positive infinity in the answer because it goes up. And finally, limit x goes to negative infinity of f of x to give you negative infinity as the answer. So you have 4 motions possible, right? And you have 4 outcomes, right? It's either right up, right down, left up, and left down. So that's the end behavior of the function. And you can use this. So now I'm going to, well, I already have the example for it with this one. I'm just going to put x cubed. Reina?
Are those always going to be the end behavior, since you said that sometimes it swings around?
Yeah, exactly. Because sometimes these are the end behaviors when you have function do that. The sine and cosine do not have this behavior because they are periodic functions.
So those wouldn't be the end behaviors.
Exactly. They are not end behaviors for these. They're also not end behaviors. Even the okay, that's a little bit. Let's talk about 2 examples here, which are very similar the way they look, but they are much different in the eyes of calculus here. So let's start first with considering x cubed. So this is your x cubed. So what we, dare I say, clearly see is that the function, right, will have these 2 end behaviors. I'm going to circle, oh, x cubed, get out of here. I'll just write f of x equals x cubed because I want to use purple over here, circle it and bring it out to say that the limit of x cubed as x goes to infinity is what? Positive infinity, yes. And then here in blue, the other end of the function is what? Limit of x cubed as x goes to negative infinity, because it goes to the left all the time, is what? Negative infinity. And we're good to go. So x cubed. Now the important aspect here is that this goes to infinity. And I already said it doesn't work on tangent, even though the principal tangent looks the same way. Can anyone tell me why this concept does not work on tangent? As I draw a tangent over here. That's it. Nice. I draw these vertical asymptotes and I draw a single tangent squiggle here. Can I even write this? You see this? So I have to stop. I can't even write this part. Forget about the rest that I have to put a tangent over here and maybe some answer. This makes no sense. Just writing x goes to infinity makes no sense because I have a vertical asymptote at pi over 2. It stopped there. It can't go to positive infinity. Make sense? And I just noticed that these things disappeared as, right? Even though I erased all those courses. So that's not an issue. So I can't even write this because there is a wall at pi over 2. Tangent never goes to infinity. So it does not work for tangent. Oh, come on. Does not work for tangent. Erase this. Erase this. And the rest should be good, right? Yeah. Okay. So end behavior does not work on every function under the sun. Only those that actually go to infinity. So this doesn't work on any of the trig functions, for instance. And then also it doesn't work on any of those that approach horizontal asymptote, but that's the second part of this lecture. So let's go and talk about horizontal asymptotes. Horizontal asymptotes. So definition, formula, theorem, whatever you call it. The function f of x will have horizontal asymptote at y equals L if the limit x goes to either positive or negative infinity of f of x is L. So you solve the limit and you get a finite value. That finite value is the horizontal asymptote. Some of you might remember from your pre-calculus course those 3 rules for horizontal asymptotes. When you divide polynomials to make a rational function, you have the exponent in the numerator is greater, no horizontal asymptote. Exponents are the same, asymptote at the ratio of front coefficients, so leading coefficients. And then if the denominator has the higher exponent, the asymptote is at 0. Right? Those are the rules that you had to memorize. Well, you don't anymore, right? So just take a moment and forget them now. Oh, you have no clue what I'm talking about? Good. You don't need it, right? So this is not just for polynomials. Those 3 rules that you might remember from pre-calculus, those rules were only for rational functions when you divide 2 polynomials. But horizontal asymptotes are present in inverse trig functions. They are present in e to the x. Exponential functions have horizontal asymptote and so on. So you need to be able to figure out horizontal asymptote for any function under the sun, not just, well, and beyond sun, in the galaxy, let's say. So you need to be able to calculate any asymptote, not just for rational functions. So this is the definition, and this is the formula. So now we can go and work on a basic example first, clearly, 1 over x, and then upgrade from there. So if I have y equal 1 over x, you already know, because it's a basic function, what the graph looks like, and you know that you have horizontal asymptote at 0, because you have eyes and you just look at it, right? And you see it there. So now, if I take a look at the limit as x goes to positive infinity of 1 over x, well, positive infinity is to the right, and you see that the y value falls off as you are moving along, giving you 0 as the answer. Now, it is very important to understand this concept, because the concept helps us with understanding division. If you take a look at this example, what happened to those tissues? Oh, well. I guess I'll have to rip someone's homework. Right now, you don't need this, right? I'll just remember that you had it. So, I'm just kidding. Everyone's like, yo, please do it. I've never seen Professor do it in class. I'll just take the paper. All right. Behold the paper over here. It's 1 unit. Dividing by 1 means create the pile to put everything you have on that pile. So I have 1 paper, and if I want to create 1 pile, I will divide 1 by 1, because I'm placing this on 1 pile, and there you go, 1 by 1 is 1, and I have 1 paper. But then, if I want to create 2 piles having 1 paper, I clearly have to divide paper in halves. And the answer is half. So I have 1 unit, which is the numerator, but I want 2 piles, which is the denominator. So when I divide 1 unit into 2 piles, I get a half for each of the piles. So here's pile 1, pile 2, each one contains a half, and then when you put those halves together, you get your 1 back. Now you can keep dividing, right? And look what's happening with the result. Remember, you start by stating that you want 1 paper in 2 piles, and you get 1/2 to be the answer. So this side is the computation, the physical representation of what you want. 1 thing in 2 piles. On this side is the answer. You have a half of the thing in each of the piles. If you divide by 4, you will have 4 piles, and each pile will contain a quarter. So, a quarter, and then an 8, and then, this is very important to understand actually, a 16th. This is 1 over 32. What is happening, guys, physically with your object that was 1 before? Getting smaller. Remember that one. 1 over 64. 1 over 128. There are 128 of these in this. 128. Here's 1 over 256. That's a 1 over 512. 1 over 1024. And finally, I'm bored. 1 over 2048. 2048 of these little guys to, do it. So, what's happening with this? You see that as x goes to infinity, what is happening with that 1 unit you have? Magic, right? Goes to 0. Now, also note your language. Pay attention to it. It goes to 0. So the answer is 0 only when you are at infinity. So we are going to say that the limit of 1 over x is equal, as x goes to infinity, is equal to 0. Now this becomes a basic building block of what we are going to do for the rest of this section, because we are going to try, well, actually not this one, the one that is a little bit enhanced. I'll write it here. A limit as x goes to either positive or negative infinity of 1 over x to the whatever power you can master there is equal to 0, as long as n is obviously larger than 0. And we are going to use this a lot in our calculations. Now, I hope you've seen and understood the experiment which confirms this, where you take one unit and you start cutting it again and again and again and again and again, right? Maybe you also caught why division by 0 is not possible, and you simply can't make it work. Remember what the goal of division was: to take one object and put it in this many piles, right? Now, you would all agree that this object is in one pile right now. It's one place. Dividing by 0 is asking me to take this object and put it in 0 piles. Right? Mind blown. You can't divide by 0, because you can't take a physical object and put it in 0 piles. You can put it in one pile, you can put, right? You're in one pile right now. Right, it's just a pile of you. Right? We can put you in multiple piles, which would be really gory and bad, but it's possible. What I cannot do is put you in 0 piles. And that is something that that is division by 0. So hopefully you understand that piece now. So the whole thing in calculus here, we're going to focus on this result a lot. As you cut the object infinitely many times, the result on the other end is smaller and smaller and smaller pieces. If you keep cutting to infinity, you will eventually reach 0. So that's the notion of the horizontal asymptote. At infinity, the function has to approach that value. So now we can go and consider a whole bunch of problems trying to figure out where these asymptotes are. So for instance, you want to take a look at function f of x equals to x plus 3 divided by x squared minus 1. Since x squared minus 1 factors into x plus 1, x minus 1, and none of those cancels, we immediately know we have two vertical asymptotes. So that should be, that knowledge should be available to all of you, because that was the last class. So two vertical asymptotes, definitely, because we have two candidates, and none of the factors canceled with x plus 3, because none of them is x plus 3. So we have two vertical asymptotes. Now what's happening with horizontal asymptotes? Well, for horizontal asymptotes, I have to run my calculation, so I'm just going to say limit x goes to infinity of x plus 3 divided by x squared minus 1. And if you have rational functions, like you have over here, there is just one simple trick to solve it. And that is figure out what is your highest exponent term, and you divide each term by the highest exponent term. Highest exponent term is clearly x squared. So, in the next step, you are going to divide each by x squared. So if you need to write this in your notes, right, verbally, right, verbals, words, if you want to use words, you will just say divide each term by the highest exponent term. And that's the end of the story. Divide each term by the highest exponent term. Obviously, if you don't read your notes ever, don't bother. It's just a waste of energy. You work hard during breakfast, right, to get those calories up, just to waste a half a calorie on something you'll never read. So, divide each term by the highest exponent term. Only the term with the highest exponent in it, whatever you wanna verb it. Well, since I used the wrong word earlier and made up the word that doesn't exist, why not continue using it, right? All right, let's unleash algebra upon this. What do we have? We have limit x goes to infinity, and we see that x and x squared cancel to 1 over x, plus 3 over x squared survives. These two puppies cancel to 1, and then 1 over x squared.
Did we ever see this before, or is this new for calculus?
New. Mm-hmm. The procedure, it's a limit, right?
No, I mean the dividing by the highest.
No. Nope, that's new. That's the way to solve this limit. You have the limit when you plug everything in. You can't plug in infinities. So, because you can't plug in infinities, everything that we do in this section will be something that you haven't seen before, because you are used to plugging in values from pre-calc so far, right? All right, so we have this. So now I have the situation where I get to use this. Yay, right? Do you see that I'm dividing 1 by x, dividing 1 by x squared, and dividing 3 by x squared? Well, would we all quickly agree that if I have 3 papers and I cut 3 papers infinitely many times, I'm still going to have 0, right? Because 3 does not stand a pair to infinity. So all of these go to 0, and the only one that survives is 1 in denominator. So what do I get? I get 0 divided by 1, and the answer is 0. Now this matches that those words you learned in pre-calc 1. If the higher exponent is in the denominator, the horizontal asymptote is y equals 0. Ta-da! Right? So there's no need to keep those in your head. If you do, well, great. Is that a chair missing over there? Yeah. All right. We're gonna get this one. I don't want to trip over. All right. So, yeah, that's that. Let's take a look at problems that your textbook might ask you to do. Ah. Forgot to log on. Chapter 2, limits at infinity. All right. So we're going to take a look at few of these. First, some of the vanilla examples we have, and then some scarier stuff eventually. So let's start with problem 10. Cheap as it can be. Limit x goes to infinity of 5 plus 1 over x plus 10 over x squared. What would be the answer? Five. Very good. Because both of these go to 0 by the definition we had, so 5 is the only thing that survives. We all clear? So we are using this. 1 over x squared, or 10 over x squared, doesn't matter what it is. The number on the numerator really doesn't matter. And then there is this nice spin to the problem, just to see if you are paying attention and you know what's happening. So the problem looks like this. Plus, and then they have this really cute term. It says sine to the 4th x cubed divided by x squared. Why?
Over, like, that's all connected to one and something else, so it's there anyway.
Yeah, there are math majors that know pre-calc too. As soon as you have a trig sine or cosine, the range of sine and cosine functions is 1. So, believe it or not, whatever you write here, as long as it has sine and cosine, is always smaller than 1, or equal to 1. It can't go over 1. So technically, this term is as good as you having 1 over x squared. So, all of this term goes to 0, this term goes to 0, and the answer is 5 again. And I was just going to put this because sine, I'm going to put f of x. So because sine of whatever you can master here is bounded by 1. Now this means that -1 less equal than sine of whatever function you stuff inside less equal than 1. So this term is just as good as 1 over x squared. And we had this within the squeeze theorem as well, that the sine is bounded, so. Yep. And then we have these beautiful problems that are relative term, beautiful for me. You might not like it, I don't know. I want to find a nice one. Nope. Alright, they don't have any of theirs. So I'll solve, I guess, go through 41, and then you have 42, 43, and 44 to enjoy on your own. What's happening with the limit x goes to infinity of 4x cubed plus 1 divided by 2x cubed plus square root of 16x to the 6 plus 1. At which point you probably go, why? Because we can. That's why. I mean, the answer is clearly 2/3, but how do we get that? Yes?
Just you guys, is the first step you have to divide everything by x? Because, that would just like reading it before.
Not x, why x to the 6th?
Just like the highest.
Is it?
You can reduce it. Right? You take 4x to the 3rd and 1x.
What's the highest exponent in the problem? 3. Square root of x to the 6 is x to the 3. It's of that order. You cannot take that square root because of +1. You cannot take the square root. But the order of it is x cubed. X cubed plus another x cubed and another x cubed over here. All of these are x cubes across they are the same order. Now you can't take the square root because of the thing. But it's not going to prevent you from dividing every term by x cubed. Now what happens with the x cubed as it undergoes the square root? What happens to it? What's going to happen when I take the x cubed and I put it under the square root? It becomes x to the 6th. And that's how that term dies. So, let's go. We are going to divide in the next step. You have to leave a lot of space here because it's division. So we have 4x cubed plus 1. And I'm going to divide by x cubed in red. Then I'm going to jump here, say 2x cubed plus square root of 16x to the 6 plus 1. And then over here I am dividing by x cubed. And hi. And why am I dividing over here by x to the 6?
I don't know.
I'm just messing up. So I am dividing by x to the 6 because when x cubed undergoes the square root, it will, so I'm just going to extend this square root now with the red. As soon as the x cubed goes under the square root, it becomes x to the 6th. So now, we first do the algebra here, where I have 4 plus 1 over x cubed. We know that 1 over x cubed is going to die, right? Limit to infinity, that goes to 0, so 4 survives. Yes?
Why is it x to the 6 under the 1?
You have to divide every term. There are 2 terms. X, if you divide the entire fraction by x cubed,
No,
then...
like x,
Oh, this is a 3 over here. Here. It's a 3.
It looked like a 6.
I see I made a mistake of moving the chair all the way up there. You can sit here with me if you want. You're welcome. So clearly it's a 3. Yeah, go ahead, zoom in your notebooks like this. Now look what you did. I can't get the standard size. There we go. Yes?
You're leaving it as x to 6 because the square root of that is x to the 3rd.
Mm-hmm.
That's why.
When you have a square root of x to the 4th, you get x squared. Right? If you have x in front of the square root and you want to go under, it better be 2x squared, because when x squared goes outside, it becomes x. Right? So when you're getting out of the square root, you divide exponent by half. When you're going inside, when you're stopping inside, it becomes, exponent becomes times 2. You're not squaring the exponent, you're multiplying it by 2, because it's a square root. So 3 times 2 is 6. And I have the square root of 16 plus 1 over x to the 6. At this point, we unleash the limit. This dies and this dies. And we are left with 4 over 2 plus square root of 16. 4 over 2 plus 4. 4 over 6. And as I promised, 2/3. What is the way I do these problems mentally? I look at this and I say, that's x cubed, that's irrelevant, that's x cubed, and this over here is the order of x cubed. Since they're all x cubed across the board, then I know it's just a game of front coefficients. So in my head was 4. As soon as I see this problem, I see this. Like that. And I knew it was 2/3 right off the bat. Again, years of training. But you can, when you know the rules, when you know the procedure, you did enough problems, because it's all practice, obviously. It's like making a pie. Right? You practice making a pie, and then eventually you have a perfect pie. You practice that? No? Just do this. Have a perfect pie every time. So practice. Practice makes perfect. So the same thing goes over there. Practice, 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 and you will be able to instantaneously answer these questions. You want another one of these? All I heard was yes, so let's do it. 42 follows closely behind. Limit x goes to infinity. The square root of x squared plus 1 divided by 2x plus 1. What's the answer? Clearly? 1/2, clearly. Okay, good. Now get it. Do the steps. Do the steps between the problem and 1/2. Oh, come on. I have to go and fix things. He does not like these vertical lines, no matter how many times I draw. All right. Hopefully everything is there. Oh, I know. I think I can force it to. Let's try this. I was cleaning up. Watching cleaned up all of my. Maybe I should do that. Just frequently restart. Kept everything. Well, we'll try that. So we know the rules. We are going to divide everywhere by x as the highest exponent. But when that x undergoes the square root, it will become x squared. So limit x goes to infinity. Over here, I'm going to have x squared divided by x squared plus 1 over x squared. And over here I have 2x over x plus 1 over x. When we apply algebra first to cancel off all of the things we don't need, we get 1 plus 1 over x squared, and we get 2 plus 1 over x. Now in the limit, these guys are going to die again because of this one. All right? This one says 1 divided, or any number over here on top, any number divided by x to whatever positive exponent is going to go to 0. So that's why all of these guys are gone, and what you are left with is square root of 1 over 2, which is 1/2. Observe that these two steps do not have limits. And observe that each one before that had a limit. You not writing limit is pretty much the same like not writing a minus sign or not writing a multiplication, division, whatever operation. These are called operators, they're not called operations. But still, it is an instruction of what you are to do. And once you do it, you don't write it again. The common symptoms in algebra of, bad notation are square root of 9 is equal to square root of 3. Writing the, right? Do not write limit in front of the answer. Because square root of 9 is simply 3. You used up the square root to change 9 into 3, so you don't get to write square root again. You used up limit to get these guys into 0, so you don't get to write the limit again. So you can't write limit here because you used it up to change this mess into this. Fair? Just like you used square root to change 9 into 3. So notation wise, because my allergies kick in as soon as I see limit 1/2 and then box. No, it's just 1/2. You used up limit to get to that 1/2, and that's the end of the story. Are we all good on that now? So please do not box LIM in any of your answers on the lab test and so on, because this is your answer that you box and you're done. Unless I'm asking you to state the formula for vertical asymptote. If the question says, let's say, I don't know, 5A says state the formula for vertical asymptotes. Clearly says word formula. You are going to write, okay, a limit x approaches a plus or minus, whatever, from left or right, of f of x is equal to one of the infinities. And you box it. This is the only case when you are going to box a limit as the answer, because it's asking. Otherwise, it's just a part of your calculation, and you better not have it at the end, because it doesn't belong there. You used it up. Oh, come on. Huh. Weird. Sorry, OneNote is clearing up from the last time it was opened. Great. I'm gonna stare at that screen more than anything else. And why is the stream red? Video output low. It's just when the network is moody, this computer just goes crazy. It loves to be connected to internet 100% of the time. Time to analyze e to the x and be done with this lecture. So we have f of x equal e to the x. So what's happening here? Well, if you look at the graph, you have limit x goes to negative infinity of e to the x to be equal to 0, which is horizontal asymptote at y equals 0. And you also have limit x goes to positive infinity of e to the x to be positive infinity, which is what? What is it? Is it a horizontal asymptote? No. Is it a vertical asymptote? Yes or no? No. Good. So what is it? Nope. Yeah, exactly. Let's go. Facepalm. Good. Make it crisp. Psh. So it's just end behavior, right? It's increasing to infinity. Done deal. And that's it. I hope you're not disappointed. Bye.